Welcome to the Deep Dive. Today we're tackling something huge, antibiotic resistance. It's a growing global challenge, and we really want to get into how bacteria actually develop this resistance. It's crucial stuff, but often misunderstood.
Exactly. And our focus today is the Ambler classification. Sounds a bit technical, maybe, but it's a system for sorting out beta-lactamase enzymes.
Beta-lactamases.
Yeah. And understanding this is, well, it's absolutely key to knowing why some antibiotics just stop working, and maybe more importantly, what treatments we can still use effectively. So our mission is to give you a kind of shortcut to grasping this vital knowledge.
Okay, great. Let's unpack that then. First things first, what exactly are beta-lactamases?
So they're enzymes, basically proteins that bacteria make. And their job is literally to break down our beta-lactam antibiotic.
The big ones like penicillins?
Penicillin, cephalosporins, carbapenems, yeah, the largest, most widely used class. It's how bacteria fight back, a sort of chemical warfare at the microbial level.
Got it. So the Ambler classification helps us sort these bacterial weapons out.
Precisely. It groups them based on, well, two main things. Their clinical impact, like which specific antibiotics they can defeat, and also their genetic origins. We're going to walk through 5 key groups today.
Okay, let's start. What's the first group?
First step, we have the broad-spectrum penicillinases. These were sort of the first line of defense bacteria developed. They're still very common.
And they take out penicillin, obviously.
Right. All penicillins, plus the first and second generation cephalosporins, they render those ineffective. Think of it as the classic bacterial resistance mechanism.
And genetically. Any specific markers there?
Yeah. Typically, you see genes like TEAM1 and SHV1. Those are mostly in gram-negative bacteria. Then there's PC1, which you find more in gram-positive Kachi.
Okay, so even this classic resistance is still relevant.
Oh, absolutely. Their persistence really drives a lot of antibiotic use and creates pressure for more resistance. We focus on the superbugs, but these foundational ones are still a major part of the picture. And that gram-negative versus gram-positive difference matters for treatment and spread, too.
Right. Okay, so after the penicillinases, where does it get more complex?
Well, here's where it gets really interesting, as you say. Extended spectrum beta-lactamases, ESBLs.
ESBLs, I've heard that term. That's a significant step up for the bacteria, isn't it?
It is. It's a huge leap. These enzymes confer resistance to third-generation cephalosporins, drugs like ceftriaxone, which we often rely on for, serious infections.
So if you get that lab report back, the antibiogram, and it says ceftriaxone R for resistant.
Yeah. If you see ceftriaxone R, chances are very high that an ESBL is involved. It's a strong indicator.
And treatment then becomes much harder.
It does. For ESBLs, you often need to move to newer strategies, things like the beta-lactamase inhibitor combinations, like, adding a drug to protect the main antibiotic.
Like Piperacillin-Tazobactum.
Exactly, or similar combinations. Or sometimes you might even need to consider colistin-based therapy, which has its own issues. Genetically, these ESBLs are often derived from those earlier TEM or SHV genes, or they can be CTXM types. And a big part of the problem is how easily they spread on plasmids between bacteria.
Okay, wow. So ESBLs are a major hurdle. What's the next category?
Next, we have the AmpC enzymes, sometimes called cephalosporinoses. They present a slightly different challenge.
How so?
Well, they make bacteria resistant to drugs like cefoxitim and cefotatin. But interestingly, some fourth-generation cephalosporins, like cefepime, can actually still work against certain AmpC producers.
That's a big counterintuitive. Cefoperazone still works. Why is that? And does that make them tricky to deal with clinically?
It's a good question. The cefoperazone activity is due to its stability against hydrolysis by many AmpC enzymes. But yes, they are tricky. One reason is that AmpC production can sometimes be inducible.
Inducible, meaning it doesn't always show up on tests.
Right. The bacteria might only produce the enzyme when exposed to certain antibiotics, so it might look susceptible initially. This really highlights the need for careful interpretation and, looking at the bigger picture. It often pushes clinicians toward using carbapenems or maybe cefepime if they suspect AmpC based on the pattern of resistance.
Okay, that makes sense. Nuanced decisions. Now, carbapenemases. The name alone sounds ominous.
And it should. These are a really major concern. Carbapeneses, as the name suggests, break down carbapenems.
Which are often our last resort, antibiotics, right? For the really severe multi-drug resistant infections.
Exactly. So when you see carbapenems R on an antibiogram, that's more than just a red flag. It's a serious alert.
What does that mean practically for a patient with that kind of infection?
It often means the situation is dire. Treatment options become incredibly limited, sometimes forcing the use of older, more toxic drugs or even experimental therapies if available. It puts the patient's life at immediate risk. Genetically, we're often looking at enzymes like KPC.
KPC, Klebsiella pneumonia, carbapenems.
That's the one. Very common in K. pneumonia, but it's spread. And also OXA-derived enzymes, particularly in Acinetobacter species. Knowing the specific gene involved can sometimes help predict the resistance pattern and guide the very limited treatment choices.
A stark picture. Okay, is there one more group?
Yes, the final group we'll cover are the metallo-β-lactamases, or MBLs, another group that causes carbapenem resistance.
So, similar threat level to the other carbapenemases.
Generally, yes, because they take out carbapenems, but there's a key difference in treatment potential. While they confer resistance to most beta-lactams, including carbapenems, bacteria producing only MBLs are usually still susceptible to aztreonam.
Aztreonam, a monobactam. That's interesting. Why does that work?
It's down to the enzyme structure. MBLs use zinc ions for their mechanism, which is different from the serine-based mechanism of KPC or ampios. Aztreonam isn't broken down by these metallo enzymes, so aztreonam-based therapies, sometimes in combination, can be an option.
And what are the genes for MBLs? I feel like I've heard of some infamous ones.
You probably have. NDM1 is the most notorious one, New Delhi metallo-β-lactamase, but also AmpC and Vim types are significant MBLs. Seeing these genes points towards MBL production.
So knowing the specific type MBL versus KPC really matters for treatment choices then?
Absolutely critical. That difference, that aztreonam susceptibility for MBLs is a perfect example of why understanding these classifications and the underlying genetics, often through antibiotic susceptibility testing or even faster molecular tests, is so vital. It directly guides therapy in these very difficult situations. And, it gives researchers clues for designing new drugs too.
Okay, so pulling it all together, we've gone through these different classes, these enzymes bacteria use to fight back.
Yeah.
Broad spectrum, ESBLs, AmpC, carbapenemases, MBLs. It really shows how sophisticated their defenses are.
It really does. This deep dive into the Ambler system, I hope, clarifies just how bacteria adapt and evolve. And understanding this isn't just academic. It's vital for the scientists working on new antibiotics and, crucially, for the doctors and pharmacists on the front lines making life-saving decisions every single day based on this kind of information.
It's an ongoing arms race. As bacteria keep evolving these defenses, it makes you wonder, what are the next strategies going to be? How do we stay ahead? And how will knowing about specific markers, like NDM1 or KPC, change how we practice medicine in the future?
Exactly. Those are the big questions we need to keep asking.
Definitely something for all of us to think about. Thanks for breaking that down. My pleasure.